Hello everyone, welcome to Sri Chaitanya Academy and I welcome you to this brand new session of transition course for chemistry where in the last class we discussed about the periodic table. I told you about the various groups that can be arranged. In today's class, we will move forward to one important property of elements in the periodic table, right, which is atomic radius. Before that, some small things which I did not tell you in the last class. Let me pay heed to those things as well. Right. So this first S block element group, this first group is called alkali metals. The second group is called alkaline earth metals, right? This last group is called noble gases. This 17th group is called halogens, right? And D block elements you already know, right? So these are some common names they have given to it, right? Now let us move forward to our today's topic, which is the definition of atomic radius. So what is actually atomic radius? Simply first understand it, then I'm going to define it for you also. So here you have a nucleus. Around that nucleus you have a number of shells, right? This is one shell, this is two shell, this is three shell. In this, the outermost shell, right? This is the outermost shell. Outermost shell, which is also called the valence shell, right? Now, distance from the center of the nucleus, from here to outside, this distance is called atomic radius. So distance in an atom, distance from the center of the nucleus to the outermost shell or the valence shell, that distance is called atomic radius, right? So simply I can write it down here. Distance of the center of nucleus to the outermost shell is called an atom's radius, okay? It is called an atom's radius, or you call it the atomic radius. That should come to your mind, right? How many types of radius is there? One is covalent radius. Second, metallic radius or crystal radius. Metallic radius, we also call it the crystal radius. And fourth is van der Waals radius, right? So these three types of radius are defined. Now let us understand one by one what do they mean. So the first one is your covalent radius, right? So understand that covalent radius is defined for what? It is defined for covalently bonded molecules. Now, how do you get a covalent bond? Understand that when two orbitals overlap, it is then that you get a covalent bond, right? So, if I have suppose an s orbital, right, here, so one s orbital and another s orbital, if they overlap like this, then we can say that a covalent bond has formed. Now what you have to do is mark the centers of these orbitals, correct? Now, after you mark the centers, draw a straight line, from their centers, and then half of that straight line, this part is your covalent radius. This is your R covalent. Okay. So if this is A, this is B, then R covalent is AB by 2. And this is defined for two covalently. You can say that defined only for covalently bonded molecules. Okay. Now, after this, we have the metallic radius. Metallic radius, or we also call it the crystal radius. So why do we call it the crystal radius? Let us get to that. In metals and in crystals, what happens is covalent bond is like this, but in metals and crystals, the atoms are just touching each other. They are not overlapping. They are not like this. They are touching each other. Because they are touching each other, I am going to draw them like this. Right? Just touching each other. Now again I will mark their centers, draw a line, and half of that, right, half of that this particular thing is called R metallic. Okay. So if this is A, again this is B, the R metallic or crystal will be A B by 2 again. Now after this, I'll move on to the third radius, which is little bit different, little complicated, but you have me here, right, to make things easier for you. Van der Waals radius now. See, when two atoms overlap, what do you get? You get a molecule, right? So if I have hydrogen atom overlapping with another hydrogen atom, you will get an H2 molecule. Similarly, if I have a chlorine atom overlapping with a chlorine atom, I get a chlorine molecule. Right? I get a chlorine molecule. Right? Chlorine molecule I'll get. So now, earlier I was discussing about two atoms, whether overlap or in contact. Now I'm going to discuss about two molecules, two separate molecules. So let me do that. So if I have, suppose, chlorine, one molecule here, and I have chlorine, another molecule here. Understand this very carefully. Now, this is the center of atom of one molecule. This is the center of the atom of the neighboring molecule, the next molecule. So then if here I will draw a line, and then I will take half of that. Now, understand that van der Waals radius, the last one, this is a radius between two entities or two things which are not actually bonded, but they are very close to each other. So they are close to each other. Now this part, okay, this part till here, this is your R van der Waals. Okay. Now, okay. After this, let me take one more slide. Let it be here only, or let me take one more slide. That is easier to do, right? Okay, let me go to here. Right. You go to this slide and I ask you to arrange these radius in their increasing or decreasing order. Yes, arrange these radius in increasing or decreasing order. Tell me which radius will be the maximum. Which radius will be maximum here? See, it's quite simple. See, this is covalent radius. This is metallic radius. This is van der Waals radius. So, covalent, metallic and van der Waals. So, I think you have fairly understood this. So, if I want you to arrange them in their orders, the highest will be R van der Waals, followed by R metallic, and then you have R covalent. So, the order of the radius will be this. Now, as a consequence of this, understand that the van der Waals radius is the largest, right? The van der Waals radius is the largest. We'll go to that also. So, understand the last part now here. You remember the noble gases, right? Noble gases, these gases. Now, all of these gases, you can see here, the number of electrons here are 8. So, all of them have complete octet. So, the noble gases have complete octet. So, they do not want to bond with each other or any other element. And these noble gases exist as individual atoms, means just atoms. No compounds, no diatomic molecules, they are monoatomic. So, why am I telling you this? Write one point here, that ignore the heading. Noble gases have complete octet, so they do not bond with other atoms and exist as a single atom, or slash they are monoatomic gases. So, why I am telling you this? Simply I am telling you this because if I have a helium atom and I have another helium atom, bear with me on this one, they will not overlap, correct? So, they will not overlap. So, then if I have the center here and I draw a line and take their half. So, what will this be called? This is called the van der Waals radius. And understand that noble gases, the point to write here is that noble gases because van der Waals radius is the largest, noble gases have the largest atomic radius in a period. Okay. So what I'm trying to say is, in this one, if you come from here to here, this will have the largest radius, because the radius which we are measuring in case of noble gases is van der Waals radius. So that is why this was important. So after we have done this, okay, factors affecting atomic radii. Now this heading you can take into the next part, which is the first factor which affects atomic radius is nuclear charge. You have the nucleus, right? Suppose many shells are there and this is the outermost shell. There is an electron here. If this nuclear charge, nucleus is positively charged, electron is negatively charged, so obviously positive nucleus will attract the negative electron. Now, more is this attraction, right? More is nuclear attraction for electron. This is ATT raised to power n, means attraction for electron. What will happen? This valence shell will come close and shrink. The valence shell comes closer to the nucleus and size decreases. So I can clearly say that atomic radius is inversely proportional to nuclear charge. More is the nuclear charge, lesser will be the atomic radius. Next, screening or shielding. This screening or shielding I have already discussed with you, but I'll repeat little bit here also. So if you have the nucleus here and you have an electron here and you have an electron here and you have an electron here also. The nucleus is actually attracting this outer electron towards this direction, but these intermediate electrons are doing what? They are repelling, right? So this electron is repelling this electron towards this side, this electron is also repelling this electron towards this side, but the nucleus is attracting towards this side. You can see the repulsion arrows are in an opposite direction to the attraction arrows, right? So here is the repulsion happening and here is the attraction happening. Because of this, attraction of the nucleus for the outer electron is reduced. This is called screening effect. This is called the screening of outer electrons by inner electrons, right? From the nuclear pull. Now, due to which this outer electron which is here, this outer electron feels a less nuclear pull. So, Z is now the atomic number or nuclear charge as we call it becomes Z effective. So, Z minus sigma, this is called the screening constant. Screening constant. Okay, this is called the screening constant. Now, screening does what? Understand that if the outer electron is feeling less pull of the nucleus, then what will happen? Then the shell can expand. It means what? This repulsion does what? It increases the size, right? So, screening actually does what? Screening is directly proportional to radius or size. Remember this. So nuclear is trying to pull the valence shell, but the inner electrons are repelling it out. So nucleus is reducing the size, outer electrons are increasing the size, right? So both work in opposite directions. So let me just tell you this in short. Z effective is inversely proportional to size, and your screening is directly proportional to size. Remember that? Something like this. Now, here, one more thing I want to discuss. That's why I will take another slide. Okay, it will not come here. I need the slide here. Now, one more concept I would like to tell you, that the screening are soldiers, the screening electrons are soldiers which are protecting you from the enemy. The enemy is nucleus. There are the screening electrons, and this is the outermost electron, right? More closer is this electron to this nucleus, more it will be able to shield this outer electron. Understand this? More closer is your army to the enemy, more easily it can protect you, right? So what I'm trying to say is, more closer is the screening orbital to nucleus, better is screening, right? And we know that in terms of closeness, S is the closest, right? Followed by P, followed by D, followed by F for the same value of N. This is the same order, this is screening order of orbitals, right? This is the screening order of orbitals. More is this, better it is at screening. Understand this, D and F, you can see here, are poor shielders or screeners. They are very poor. If you have a D and F army person defending you from the enemy, you will most definitely die in that war, or you will lose it, because D and F orbitals are very poor shielders. Why are they poor shielders? Well, understand that if suppose you have 5 army men and here is my enemy and I am the king. So these 5 army men will just stand in front of me, all 5 together will be able to protect me better, right, from the enemy. But what if these 5 army men are spread over a large region? One army person is in the other building, the other army person is the next building, one more is in front of me somewhere, so they're very far apart. Then will these army people be able to protect me from the enemy if they are far away? No, right? That is the issue with D and F orbitals. D and F orbitals are spread over a large area, due to which there are poor shielders, right? So they will not shield the outermost electron from the nucleus's pull. Understand this? That is why if you have D and F orbitals as shielding electrons or shielding army, then the outer orbital will feel the full nucleus pull and the size will decrease. So if suppose this was D or F, this inner one, then this size would have decreased. Okay, shielding will not have any effect. Something, because of this poor shielding of d orbitals, you get something called d block contraction. What is that? We'll see that. Now the effect of this d block contraction, let us take the first series, which is the fourth period, right? So fourth period you have scandium, right? The outermost shell here is 4s. So you have 4s2, 3d1, 3d2, 3d3, 3d5, 3d5, 4s2, 3d5, 4s2, 3d6, 4s2, 3d7, 4s2, 3d8, 4s2, 3d10, 4s1, and finally this is 3d10, 4s2, right? So you can see the inner orbital is d and d orbital is getting filled. Now because of this d orbital getting filled and d being a poor shielder, you will see that the size of this series, the size of these elements keeps on decreasing, and that decrease is much more than normal. Now, understand that after this, what is coming? After zinc here, if you see the periodic table, let me go to the periodic table. You're getting the 13th group, right? You're getting the 13th group. Now what happens is, as you move from aluminium to gallium, now aluminium has internally 2s, 1s, 3s orbitals protecting it, right? 1s or 2s orbitals protecting it inside, but gallium has this complete d orbital protecting it. Now d orbital is not very good at protection. So what happens is, this gallium feels nucleus's full force, and as you go from aluminium to gallium, what happens is the size remains same, right? The size remains same, right? So okay, there was some technical issue, so I'm back here now. So let us see the group 13. Group 13 is right now. Now the 3D series comes here. Normally, when you go down a group, what is happening? If you write the electronic configuration of boron here, this will be 2s2, 2p1, this is 3s2, 3p1, this is 4s2, 4p1, This is 5s2 5p1. This is 6s2 6p1. Understand that as the principal quantum number keeps on increasing, what is happening? Your shell is increasing, right? First shell, n equals to 2, n equals to 3, n equals to 4, n equals to 5. So the distance should increase. So as you go down the group, normally size should increase, right? Because you can see 2, 3, 4, 5, 6 is increasing. But something remarkably different happens here. What happens here? Let us see. This does not happen. Size does not increase normally. How does it increase? See, from boron to aluminium, size increases. But from aluminium to gallium, size remains same. Right? Again, from gallium to indium, your size increases. And again, from indium to thallium, size remains same. So what I'm essentially telling you is that aluminium and gallium size is approximately similar. Similarly here, indium and thallium size is approximately similar. Why is it happening? Understand that, here we know that because d orbitals are coming, the atomic number has increased. Remember that as you go down the group, the atomic number increases, and because atomic number increases, the number of protons inside the nucleus increases. So nucleus's pull increases, right? So nucleus's pull increases. So from boron to aluminium, what is happening? The nuclear pull is increasing, but the internal electrons are shielding it better, plus the distance from the nucleus is also increasing. So the distance has increased, so that increased nuclear pull does not have much effect here. So here what dominates here? Here the size dominates, or I can say the shielding dominates. And we know shielding increases size. But from aluminium to gallium, something remarkable happens. What happens is, if suppose this is aluminium, this is the gallium's valence shell, because the nuclear pull has increased, and also because these d orbitals do not protect the valence shell from the nuclear pull, this gallium, which lies immediately after the 3D series, experiences a large nuclear pull, and it is pulled, so much pull it experiences that it becomes close to aluminium's valence shell. Now this is gallium's actual valence shell. Because of this, both aluminium and gallium have the same size. Now this is fine, but what the hell happens here? Well, for that, go back to the periodic table. So aluminium, gallium is fine. What happens in indium and thallium? This happens. What happens? This happens. F block elements. Now F orbitals are much more spread out than the d orbitals. They are way poorer shielders of nuclear charge even than d orbitals. So that is what happens here. Right? Here you have F block. Now this F block is much more poorer shielder. So what happens is, from indium to thallium, same effect happens, and now you will have indium and thallium having the same size, right? If this is understood, now let us give a name to it. This effect here, right? This effect here, this is called D block contraction, and when it happens due to F, right, the effect in this point is called the F block contraction. So let me just write it down clearly here. Boron, aluminium, gallium, indium and thallium. From aluminium to gallium, what works? D block contraction, due to which size is same. From indium to thallium, what works? The F block contraction. Contraction is that, okay, it was this much, it contracted. So again the size is same, right? And easily I can say that here, from here, size increases, here size same, and from here to here increases, and here to here is again same, right? So this was the complete summary of, so that is the F block contraction. I have already told you. You can write it down if you want. Due to poor shielding by inner F orbital electrons, the valence shell feels an increased Z effective or nuclear charge, which contracts the valence shell and reduces the size of the atom, right? So if you want to write it in words, you can write it like this, but that is your F block contraction. Now the next thing that affects the size is the number of shells. This is quite obvious. This is the nucleus. N equals to 1, N equals to 2, N equals to 3. You can clearly see that as the principal quantum number N or the shell number is increasing, the distance, so I can say that as shell N increases, what is happening? The distance of the valence shell from nucleus increases, so Z effective decreases, so size increases. So I can directly say that size is directly proportional to N, right? This I can easily say. Now general variation across a period. Now what happens across a period? So let me take this period. Which period this is? This is the second period. Now let us write the electronic configuration. 2s1, 2s2, 2s1, 2p, 2s2, 2p1, 2s2, 2p2, 2s2, 2p3, 2s2, 2p4, 2s2, 2p5, 2s2, 2p6. Right. Now, as you are going across a period, as you are going from this side to this side, what is happening? The atomic number is increasing, right? If I write the atomic number, this is 3, 4, 5, 6, 7, 8, 9 and 10. So this is your atomic number. Now atomic number increases. So you can write the atomic number increases, right? Number of protons increases. Number of protons increases means positive charge on nucleus increases. So Z effective increases. So size decreases. So as you move from left to right across a period, what will happen? Size generally decreases. That is what it should be. What is the general variation across a group? Let us take this group. Right? So this is your group 1. Always write the electronic configuration first. This is 2s1, 3s1, 4s1, 5s1, 6s1, 7s1. You can again see as you are going down the group, what is happening? The n value increases. And we know that n is directly proportional to size, right? So as n value increases, the size normally increases. But if you go to the 13th group and 14th group, there are some exceptions there because of D block and F block contraction. I've already discussed that with you. Now, so one thing we have established till now, so suppose you go from lithium to this side, your size decreases, right? If you go down, size increases. So what if I go in the diagonal direction? What happens here? Here size increases, then decreases. If this is the size, it increases, then decreases, increases, then decreases, remains the same. So in this size increases, decreases, or I can say remains same. This is called diagonal relationship. The elements which lie along the diagonal have similar physical and similar properties, some properties and similar size. So what are those diagonal relationship elements? Right, let me see it here. Write the second period, and the third period. Right. This is your group 1, 2, first group, second group, the 13th group, 14th group, 15th group. Now, which elements have the relationship? Lithium and magnesium, beryllium and aluminum, boron and silicon. This diagonal relationship vanishes. So diagonal relationship vanishes after group 13. Sorry. So after group 13, you will not have this relationship. This is your diagonal relationship. Now, Now let's talk about the period 4. Something important is there. Let us see that. Period 4 is the first D block series, which is also called the transition series. Let us write that down here. Let me make equal space for all. Right. Okay. Now, let us write their configurations. 3D1 4s2, 3D2 4s2, 3D3 4s2, 3D5 4s1, 3D5 4s2, 3D6 4s2, 3D8 4s2, 3D 1 minute. 1 minute. 3D7 4s2, 3D8 4s2, 3D10 4s1 and 3D10 4s2. Okay. Now here, if you see carefully, generally what should happen as you're going towards this side? See, understand that why in a period the size decreases? Simply because I did not explain you earlier. See, the shell numbers are not changing here. In the same shell, you are adding electrons. So essentially, distance between the nucleus and the valence shell is not changing much. If this distance does not change, but this nucleus is getting more and more powerful, it is adding more and more charge. As it adds more and more charge, the pull is more and more, and as the pull is more and more, the size actually going towards this side should decrease, and it does decrease for some time, right? Till where? Till here the size decreases. From here to here size increases. From here to here size remains same, okay, and from here to here size increases again. So how can we justify this particular order? Let me remind you of a point, that effective nuclear charge or Z effective or the nucleus's pull is inversely proportional to size. So write it somewhere here. Z effective is inversely proportional to size. This we know. And we also know that screening effect is directly proportional to size. So screening effect increases the size. Nucleus effective nuclear charge decreases the size. So both of them are working in opposite direction. This is the screening effect, increasing the size, nucleus pull decreasing the size. Screening effect is dependent upon what? It is dependent upon how many soldiers are there in front of you, how many electrons are there in front of you. That inside electron is this D, right? Initially, you can see D electrons are less. So initially, the screening effect is weak. So from here to here, what is there? The screening effect is less than the Z effective. So the Z effective dominates. As that dominates, Z effective dominates, it pulls the valence shell close and decreases the size. So that's why the size decreases. Now, as you are going towards this side, slowly but steadily, one electron is being added in the d orbital. So now the d electrons are increasing. The number of your soldiers is increasing. As the soldiers have an appreciable number, especially here, all of a sudden, the screening effect keeps on increasing. Size is decreasing, but as you're moving towards this side, the screening effect slowly is increasing. Increasing. Here it all of a sudden increases a lot, right? So that's why the size increases. Now at this position, the screening effect becomes equal to your Z effective. As they become equal, both of them balance each other out and the size does not change much. So that's why size remains same. After this, the number of d electrons in D10, fully filled d electrons, the screening effect becomes stronger than Z effective. So now the screening effect is stronger than Z effective. As screening effect increases the size and screening effect is stronger here, the size increases. So these are the logics for how size changes. Size decreases, shoots up, becomes same, size decreases, shoots up, becomes same, and then increases again, right? So this happens in the period 4. Now what is the variation across the D series? What I mean to say is, if you have this is the 3D series, means where the 3D orbitals are filled. Four D series, where the 4D orbital is filled. Five D series. Normally, when you go down a group, what should happen? The size should increase, correct? Why the size should increase? Because let us take this example. This is 3D2, 4S2. This is 4D2, 5S2. This is 5D2, 6S2. Because the principal quantum number is increasing, the size should increase. But does it? Let's find out. Till here the size increases, no problem here. But as you go from zirconium to hafnium, what happens is this star, you remember, here you have 14 F block elements, which are, repeating myself, poor shielders of nuclear charge. Because of this poor shielding, what happens is hafnium feels a increased nuclear charge, a strong nuclear charge, due to which the size from zirconium to hafnium remains same. So the atomic size or radius of zirconium and hafnium becomes similar. Same thing happens here. Here also the size remains same. This is the variation across the D series. So this further cements our theory of, this is happening due to what? F block contraction, right? Now, so after D block contraction, F block contraction, one small point I forgot here, that D block contraction is weaker than F block contraction, okay? D block is weaker because D orbitals are little smaller, right? And F orbitals are little large. For viewers who have just come in, please go to the link in the description and join our Telegram channel and Google form. Coming to the last part, which is the ionic radius. See, ions are of two types. You have cations and anions. Cations are positively charged, so suppose like sodium. Anions are negatively charged like Cl minus, right? This positive charge indicates that this atom has extra positive charge on nucleus. Due to this extra positive charge, what happens? The valence shell shrinks and size here decreases. Here this negative charge means what? This negative charge means that it has extra electrons. Due to this extra electron repulsions happen, the shielding is much better. For less nuclear charge, you have more electrons, due to which the size increases. So in total, I can say here that size is directly proportional to the negative charge and size is inversely proportional to the positive charge. As the negative charge increases, size increases, and as the positive charge increases also. Yes, this is the trick, right? Size increases as negative charge increases and size decreases as positive charge decreases. Right. So this is an example. These are isoelectronic species which have same number of electrons. You will find that all of them have 10 electrons, right? But if you want to arrange them in order of their sizes, understand that anions will always have more size than the neutral atom. So if you have a neutral atom, the anion will have more size and the cation will have lesser size, right? So the highest size will be for neon, then the size keeps on decreasing as the positive charge increases, and then for negative charges it increases like this. So as a homework, try and arrange them in order of their sizes, right? This is not there here, right? 1 minute. This will be like this. For the anions, more is the negative charge, larger will be the size. So fluoride will have the least size. With this, I end today's class. If you liked it, don't go away that much fast. Fill this Google form so that we are able to connect with you. And to get further information and a bunch of free study material, join this Telegram channel where we're going to update you of whatever classes we're going to put on Sri Chaitanya Academy channel in future. So bye for now from my side, and we have waiting for you a maths class next. So meet you there.